Okay, if we want to talk about the dimension, we'd better come up with a basis. Well, here's a basis. Now, can we prove it's a basis? Well, okay. Now, is it linearly independent and does it span? Okay, those are the only questions you have to answer to prove it's a basis. If it's linearly independent and it spans a space, it's a basis. Okay, so. Okay, linearly independent. Okay, there's your definition of linear independence. That the sum of multiples is zero if and only if all the multipliers are zero. That's all it's saying, okay? So you write this condition out, where V1, V2, and V3 are what? 1, x, and x squared. This is your proposed basis. Your proposed basis is V1, V2, V3. Now you're used to thinking of vectors as arrows or multiple, column vectors, okay? But we're generalizing the idea these are equally valid vectors because we've just proven at least the three main properties, if you wish, of vector spaces, okay? And the others can easily be proven, okay? Most of them are pretty trivial for this space, okay? So, what's this mean in terms of this basis? This means C1 times 1 plus C2 times 2 plus C3 times 3. What's the zero vector in this basis? In this space? It's your additive identity. And I don't know why I wrote 1, 2, and 3. It's 1x and x squared. Just because I get these patterns in my feeble brain and go on because I'm thinking about the next step and shouldn't be. Okay, anyway. Make sense? And this should equal I of x. Okay? Which means that C1 plus C2x plus C3x squared has to equal 0. How can that possibly be? Well, if these add up to 0, no constant can be added to non-zero multiple of x and or x squared to give you 0, right? So just by, these are all unlike quantities if you just want to go back to Algebra 1, okay? They're unlike quantities, and so you can't combine them. So unless all these c's are 0, you're not going to get 0, okay? That's all there is to it. Thus, it's linearly independent, okay? And we span P3. Well, okay, for any polynomial can be written this way, right? Any quadratic polynomial. And it has to be a linear combination of the basis vectors, right? Well, your arbitrary linear combination of the basis vectors is C1 plus C2x plus C3x squared, right? The only way this equals this yeah, I've got the C and the A mixed up. Of course, it's fairly easy to make C's into A's and vice versa, okay? And I did it wrong. That was right the first time. I don't know what I'm thinking. Let me fix it. Most of my mistakes come about because I think I did something wrong. And that's usually, no, okay. Okay, so this is right the first time, that's a C. And this is an A. So C1 equals C, C2 equals B, C3 equals A. In other words, you let this be C, let this be B, let this be A. These are equal. It doesn't matter what this one is, what numbers I've got for A, B, and C. So that this is in the span of this set. So it's a vector space, and there's a basis. That's the standard basis. It's the simplest basis because it's the one that is easiest to match up with this form.